Hello everyone, welcome to the channel Knowledge Hub. Friends, subscribe to the channel and click the bell icon for the latest update. आज हम लोग जो डिस्कस करने वाले हैं वो केमिस्ट्री की क्लास करने वाले हैं। जो केमिस्ट्री की क्लास है वो 146 क्लास है। ऑलरेडी मैं 145 क्लासेस कर लिया है। तो फर्स्ट ऑफ ऑल अगर आप हमारा चैनल फर्स्ट टाइम देख रहे हो तो प्लीज़ हमारे चैनल को लाइक शेयर और सब्सक्राइब करो सो दैट हम जो भी वीडियोस डालें वो आपके पास सबसे पहले पहुँचे। एंड सेकेंडली अगर आपको हमारा वीडियो अच्छा लगे तो प्लीज़ हमारे वीडियो को लाइक शेयर और सब्सक्राइब करो तो ज़्यादा से ज़्यादा लोग के पास वीडियो पहुँचे और ज़्यादा से ज़्यादा लोग इसका यूटिलाइजेशन भी कर सके। आज की क्लास में जो हम डिस्कस करने वाले हैं वो होमोजेनियस इक्विलिब्रिया के डिस्कस करेंगे, दैट इज एन इक्विलिब्रियम कांस्टेंट इन एट अ gaseous system that we'll discuss, and with regard of that we'll solve many of the questions here, and regarding to that we'll be finding out the Kc as well, and we know about the ideal gas equation as that we had learned before also. So all that we'll discuss, and some of the topics related to the homogeneous equilibria and the heterogeneous equilibria that we'll discuss here. So in the homogeneous equilibria, before starting with this, we have to know some of the things, some of the point related to the homogeneous equilibria here. With regard of this here, so we know about the homogeneous equilibria here. In a homogeneous system, all the reactants and the products are in the same phase. And for example, in the gaseous reaction, we can say that N2 plus 3H2 gas that gives 2NH3 here. Reactant and the product are the homogeneous phase. Similarly, for the reaction, we'll go through with CH3, COO, C2H5, that is in aqueous state, plus H2OO, that is in the liquid state, that gives CH3CO double OH, that is in aqueous state, and C2H5OH, that is in the aqueous state, and the vice versa, CH3COOH in the aqueous state plus C2H5OH in the aqueous state gives you CH3COO C2H5 aqueous plus H2O liquid here. Okay, with regard of this also, this is the vice versa as well. 2NH3 gives N2 3H2 here. In regard of this, if I'm talking about taking another equation, and that we have Fe3 plus in aqueous state plus SCN minus aqueous give FeSN SCN 2 plus aqueous here, and whereas SCN here in the aqueous state gives you Fe3 plus SCN minus aqueous here. In regard of this, all the reactants and the products are in the homogeneous solution phase. So we shall note that consider equilibrium constant for the some homogeneous reaction here. And with regard of that, if I'm talking about more further, now we'll discuss about the equilibrium constant in the gaseous state. As you can see, equilibrium constant in the gaseous state. For this, so we can express that equilibrium constant at reactions in terms of the moles concentration of the reaction and the product, and used symbols, that is your Kc for it. And for that reaction involving these gases, however, it is usually more convenient to express the equilibrium constant in terms of the partial pressure, and that ideal gas equation can be written as this is the ideal gas equation that has been written as PV equals to an RT, that you know very well, and that for V or P we have to find out, we will go to the downward, and that is N upon VRT here. With regard of that here, that P is your pressure, that is in the Pascal here, and N is the number of moles and of a gas, and V is the volume here. Okay, so this is V is a volume, and this N is your number of moles of gas, and where here this is the M we had represented, that is volume, m meter cube, and then the T we have here is that is your temperature, and that is in Kelvin, and therefore we can say that totally that N upon V, if I'm talking about totally here, that is the concentration expressed in the mole meter cube, and if the concentration C is in mole per liter and mole dm cube, and that is P is for the bar, that is the pressure for the bar, then we can say that P equals to C RT. In reference to the P equals to CRT, we can also say that P equals to gas RT, and here we can say we will put the value R equals to 0.0831 bar liter per mole Kelvin. At a constant temperature, the pressure of the gas is proportional to the concentration, that we can say here that is P is directly proportional to the gas. And for that reaction in equilibrium, we have an equation, and that the reaction we have here is H2, that is in the form of gas, plus I2 and that gives 2Hi, or we can say the vice versa, 2Hi gives the H2 plus I2 here. And we can write either that Kc equals to Hi, that is of gas, of square upon that is 2 की power, that what here it is mentioned, and that is H2 and then I2 here, because यहाँ पे कोई उनका number नहीं है, so we not make as power here, even though we can write this as well, that Kc is equals to P of Hi, that is square upon, and this is P of H2, and that is multiply P of I2 here as well. Here further, since if I'm talking about, so P of Hi, as you can see, that is equals to Hi, and that is in the form of the gas state, and that is RT. And for P of I2, we can say that P of H2 and P of I2 as well. For P for I2, we have here that is I2 gas, and then we have here RT. And for the same case, we have P of H2, then we have H2, that is in the form of the gas state, and then RT here. Therefore we can say, we can write it down as well, and that is your Kc equals to P of Hi, and that is of whole square upon P of H2 and P of I2 here. And that can also be written here in the form as we can say that that is could be written in the form of Hi gas state, and that is of whole square, and that is of RT, like a whole square here as well, and that will be upon, and that will be H2 in the form of the gases RT, and then I2 gas RT here. So we will be finding out Hi, and that is in the form of the gas state, and that will be of a square here. Then upon we have here is your H2 gas, and then I2 gas as well, and that goes off, and that is equals to K here. In this example, we can say that the Kp is equals to Kc, that is both the equilibrium constant are equal, and however this is not also the case. For example, in this reaction, we will discuss more reaction, that is of N2 in the form of the gas state plus 3H2, that gives 2NH3, and that is for the same vice versa. 2NH3 gives your N2 gas and the plus 3H2, and we will find it out the Kc here for that case also. So let's go ahead here. For N2, that is in the form of the gases plus 3H2, that gives 2NH3, and as vice versa, as I told you, 2NH3 in the form of the gases give N2 gases and 3H2 gases here. In regard of this, we'll find it out the Kp here, and as I told you that Kp is equals to Kc, and so for that say Kp equals to, that is P of NH3, and that is of whole square upon that P of N2, and then plus P of H2, that is of whole thrice in the question. So we'll putting the power. Now we'll put the value here as well, and that is NH3 in the form of gases का whole square RT का square upon N2 form of gas, close the bracket, RT dot, then another for H2, that is of G in the power 3, and then RT the power 3 here. For this we'll move ahead and we'll solve the further one, that is NH3 in the form of gases and power of 2, then RT power of 2 here. Then after that we have N2 in the form of gas, and the whole bracket close, and then if it H2, that is of gas, and then power 3, it will give Kc RT minus 2 here. So here we can see that last जब हमने किया था equation, जो कि हमारा H2 plus I2 that gives to HI वाला and the same vice versa वाला reaction किया था, उसमें हमें मिला था कि जो Kp है वो Kc के इक्वल है. इस केस में क्या है कि जो आपका Kp है वो आपका Kc के RT इनवर्स के इक्वल है. In the similar for a general reaction अगर हम बात करते हैं, so we have a general reaction that is A of A capital small a and then small b with capital B, and then it goes with a small c capital C plus small d and capital D here, and for that sake we will be finding out the Kp, and that is of P of C, that C plus, sorry, the P and D of small d upon P capital A small a, and then P capital B small b here. For this, that is equals to C small c, D small d, and then RT, that is C plus D, upon A small a plus, sorry, not plus, capital B small b, and that we have RT A plus B here. So this is the formula, this is the presentation that we will doing here, and with regard of that we'll go ahead. So here we will go, and that we'll find it out C of the small c, and that D and small d upon, that is of capital A and small a, capital B small b here, and that is equal, that is multiplied by RT. जो RT की वैल्यू थी उसको हम ऐड ऑन करेंगे, that is C plus D माइनस A plus B, क्योंकि ये इन्वर्ट नीचे ऊपर जाएगा तो माइनस पावर के साथ जाएगा, and for that sake we can say that C of C and then D of D here, and with regard of that upon we have A of A and B of B here with RT value of delta n, and which is equals to Kc RT A delta n here, where this delta n, the number of moles of the gases product minus the number of the moles of the gases reactant in that balanced chemical equation. It is necessary that while calculating the value of the Kp, the pressure should be expressed in bar as standard states of 1 bar, and we have know that from the last units we have discussed about it, and that like 1 Pascal equals to your 1 Newton meter square. So with regard of that, or we can say that 1 bar equals to 10 to the power 5 Pascal here. This is what we had learned in the last units as well, and that Kp values for a few selected reaction of the different temperature that we will discuss here, and here this is the equilibrium constants that Kp for a few selective reactants, and the reactants and the temperature as well as the Kp we have here. Here we can see, and we can go on through with that N2 in the form of the gases plus 3H2 that gives 2NH3, and for that we have a temperature in Kelvin that is 298, 400 and 500. 298 जब है तो Kp आपका आएगा 6.8 into 10 to the power 5. अगर 400 टेम्परेचर आपका है Kelvin, then it is for Kp is 41, and 500 अगर आपका टेम्परेचर Kelvin में है तो the Kp value is 3.6 into 10 to the power minus 2. For next reaction that we have is 2SO2, that is in the form of the gas plus O2, and that gives 2SO2, and 2SO2 जो है वो भी आपका same for the vice versa, this goes to and gives 2SO2 plus 3O2, एंड टेम्परेचर कैल्विन जब 298 है तो Kp आपको 4.0 इंटू 10 टू द पावर 24 मिलेगी. अगर 500 कैल्विन आपका टेम्परेचर है फॉर दिस रिएक्शन वी हैव विल गेट Kp इज 2.5 इंटू 10 टू द पावर 10, एंड 700 अगर हमारा टेम्परेचर है कैल्विन विद रिस्पेक्ट टू दिस इक्वेशन with reaction that will get 3.0 into 10 to the power 4. Now we'll move ahead with another equation, and that is your N2O4, that is in the form of gases, and it will give 2NO3 in the form of the gases, and vice versa 2NO3 जो है वो N2O4 आपको देगा, and then when it is 298 Kelvin, then you will get for this reaction the Kp is 0.98, when you will get 400 Kelvin, and then you will get 47.9 here, and of course 500 Kelvin for this reaction, then you will get Kp is 1700 here, that is 1700 as well. Now moving ahead with another one, and then we'll discuss the some of the questions here related to this topic only. So here we have a question that is your PCl5, PCl3 and Cl2 are at equilibrium at 500 Kelvin and having a concentration of 1.59 m. that is PCl3 is 1.59 mCl2, and that is 1.41 mCl5. Calculate Kc for the reaction PCl5. It will give PCl3 plus PCl2, and same for the vice versa, PCl3 plus Cl2, that gives you PCl5 here. With this respect to the solution, that the equilibrium constant of that Kc for the above reaction, that can be written as like when we are finding it out, that is Kc equals to PCl3 plus, sorry, that close the bracket, and then we have a Cl2. It will give you PCl5 here. With regard of that, PCl3 and PCl2 के value जो that they had given you 1.59 का square upon, because ये भी 1.959 है और ये भी आपका 1.59 इसका square, and then upon that is 1.41, that what they had given you here, and after that solving we will get 1.79. This will be the answer for this question here. Now we'll move ahead with another question, and that is another question that we have to discuss. The value of Kc, they had given you 4.24 at 800 in Kelvin for the reaction, that is carbon monoxide gas plus H2O, that gives CO2, or vice versa, CO2 plus H2O, when the vice versa CO2 in the form of gases plus H2O, that gives CO carbon dioxide, carbon monoxide plus H2O, and that calculate the equilibrium concentration of the CO2 का calculate करना है, H2O को calculate करना है, CO carbon monoxide का, H2O water का, at 800 in Kelvin, and if only carbon monoxide and H2O are present initially at a concentration of 0.10 mm each. Now we'll find it out the solution here. So here with this, then for the reaction what we'll get is carbon monoxide gas plus H2O, that is in the form of the gas. It will give a carbon dioxide in the form of gases plus H2 in the form of the gases. So initial concentration what they have is 0.1 m, and that is 0.1 m as well, and that is 0, and as well this is 0. Let x a mole for each of the product be formed at an equilibrium, so we'll get 0.1 into, and that is a 1 mole, and that is for this also 0.1 into, and for m here as well, this is the x here that we will multiply with it, and then after that we will be finding out here also. And for that sake we have an x multiply with m, and as well as x multiply with m as well. So where x is the amount of the carbon dioxide plus H2 at an equilibrium, so hence the equilibrium constant can be written as, like we will be finding out what's the value. Kc is equals to h square 0.1 point x square, and that is your value, and that is your equals to 4.24, and that is x equals to 4.24 and 0.01 plus x2 minus 0.2x here. With regard of that, we'll find it out of x value, that is 0.0424 plus 4.24x square minus 0.848x here. We'll find out further, that is 3.24x to power 2 minus 0.848x plus 0.0424, that is equals to 0 here. Next for this we will be finding out a is equals to 3.24 and b equals to, we'll get your minus 0.848, and then c equals to 0.0424 here. With regard of that, for the quadratic equation that we know very well in the form of the quadratic equation, that is ax to power 2 plus bx plus c equals to 0, where we will be finding out the value of x. Then we have a value minus b plus minus under root of b square minus 4ac, जो कि अगर आपने मैथ्स पढ़ी है तो you will get to know कि यह कौन सा फॉर्मूला है. We will be finding out the abstract here, and for that sake we'll use these two formulas. This is a standard quadratic equation that we are using, and this is the formula for finding out the x here. So we'll go ahead and we'll be finding out 0.848 x, and that 8, and then plus this is minus as well as under root 0.848 square minus 4, and that is your 3.24, 0.0424 upon, that is your 2a, so that will be the 324 into 2 here. So this is the formula what we are applying here, the value, and that is x equals to 0. Okay, I will write it here, 0.848 plus minus 0.4118, and that is 1 upon 6.48. When we are solving this, we'll get 0.4118, and that is 6.48 here. For the x1 value, if I'm talking about, so we'll get 0.848 minus 0.41 and 18, and that is upon your 6.48, so we'll get 0.067. For the x1, where we are doing the subtraction here, because plus 9 है तो minus 1 में plus होगा. x2 वैल्यू के लिए हम 0.848 plus 0.4118, that is upon 6.48, and we'll get 0.194 here. So this is the second value. The value of 194, that should be neglected, because it will be concentration of the reactant which is more than the initial concentration. So hence the equilibrium concentrations are which we can say that of the carbon dioxide, and in the terms of cases that what we had discussed here. Okay, so we will just write it down, like we can say that for the equilibrium case, that 6 oxide, that is of H2, and that is X equals to your 0.067 m, and for carbon monoxide, that is of H2O here, and that will be give 0.1 minus 0.067, that is equals to 0.033 moles here. So now we'll move ahead. This is the value where you can find it out, all these things. And now we'll move ahead with another question that we have to solve here with respect to this. So the question here for the equilibrium, that is 2NO Cl, and that is 2NoCl, and that will give that in the form of gas, that gives 2NO, and that is in the form of the gas plus Cl2, that is in the form of the gases as well. Where in the vice versa, 2NO, that is in the form of the gas plus Cl2 gas, that gives 2NoCl in the form of the gases here. The value of the equilibrium constant K is 3.75 into 10 to the power minus 6 here at 1069 Kelvin. Calculate the Kp for the reaction at a different temperature. So here with regard of this, we will be finding out that we know that that Kc equals to, sorry, Kp equals to Kc RT, that what we had find it out here, delta N. And for the above reaction, we can say that delta N equals to 2 plus 1 minus 2, that is equals to 1. 2 plus 1, that is 3, and 3 minus 2, we can just go ahead, 3 minus 2, that is equals to 1 here. And for that, we had find it out the delta N, so we'll just put the value. Kp equals to 3.75 into 10 to the power minus 6, 0.083 multiply, that is 1069. So what we'll get is Kp equals to, that is 0.033. This will be the answer, that what we have to find it out. Okay, now with regard of that, we'll move ahead here with a heterogeneous equilibria here. In terms of the heterogeneous equilibria here, before starting with this, or you want to know that about the heterogeneous equilibria. In the equilibria is a system having more than one phase is called that heterogeneous equilibrium, and that equilibrium between the water vapors and the liquid water is closed container is an example of heterogeneous equilibrium. You can go through with the equation, that is H2, that is in the form of the liquid, and that gives to H2 in the form of the gases here. Whereas same vice versa, H2, that is give your gas, it will gives into the change into the H2 that is in the liquid here. In this example, there is a gas phase and a liquid phase. In the same way, equilibrium contain between a solid and its saturated solution. That another equation we have is CaOH twice, that is in the form of the solid, plus aqueous, and that gives Ca2 plus, that is in aqueous, and 2OH minus, that is also in the aqueous, and the same vice versa, that is Ca2 plus O aqueous plus 2OH aqueous, that gives CaOH twice, as this is in the solid, and that gives an aqueous. It is a heterogeneous equilibrium. This is what you can say here. With regard of that, the heterogeneous equilibrium often involves a pure solids or liquid. We can simplify equilibrium expression for the heterogeneous equilibrium involving a pure liquid and a pure solid, as the molar concentration of the pure solid or the liquid is constant, that is independent of the amount present. And in the world, we can say that if the substance is X is involved, then of course X of a solid will gives off X of liquid here at that are constant. Whatever the amount we'll take as X taken in the contrast to this, you can say that X is in the gaseous state, it will give an X aqueous state will vary from the amount of the X's in a even in a given volume varies. Let us take that thermal dissociation of the calcium carbonate, which is an interesting and important example of the heterogeneous chemical equation. That will be your CaCO3 in the form of the solid state. It will give you CaO that is in the form of solid, and plus a CO2 that is in the form of the gases, and as well as vice versa, CaO that is in the form of the solid, and that is a CO2 that is in the form of the gases. It gives CaCO3 that is in the form of solid. On the basis of the stoichiometry equation, we can just write it out that Kc is equals to CaO here, solid, plus CO2 that is in the form of the gases, upon CaCO3, and that is in the form of the solid here. Since CaCO3, if I'm talking about this and CaCO, and they both are constant here, therefore the modified equilibrium for that the thermal decompositions of the calcium carbonate will be, that is Kc equals to CO2 in the form of the gases, and that is Kp equals to PCO3 here, PCO2 here. Okay, with regard of this, if I'm talking about, so yes, we'll get to know about that this shows that a particular temperature there is a constant concentrations or the pressure of this carbon dioxide in an equilibrium with the CaCO solid and CaCO3 solid here. With experimentally, it has been found that a 1100 in Kelvin, like when we are talking about 1100 Kelvin, that the pressure of CO2 in the equilibrium with the CaCO2 is and that CaCO2 as that will be yours 2.0 into 10 to the power 3 Pascal here. With regard of that, if I'm talking about, so here we'll go ahead. Therefore the equilibrium constant at the 101 10 Kelvin for an above reaction, we will be finding out the Kp value, and that will be the Kp equals to Rp, that I tell you PCO3 here, PCO2, so that will be the 2 into 10 to the power 5 Pascal per 1 10 to the power 6 Pascal, and that is equals to 2 here, 2.00. Similarly, in this equilibrium between the nickel carbon monoxide and the nickel carbonate, that we can carbonyl that is used in the purification of the nickel here. So that the equation we have. So here with regard of that, if I'm talking about, so where we have another equation, that is your Ni, that is in the form of the solid here, and that will plus 4CO carbon monoxide, and it will give NiCO on, that is 4 in the form of the gases here. So with regard of this, if I'm talking about the equilibrium constant is written here as in the form of, let me finding out the equilibrium constant, that is Kc equals to NiCO4 upon CO, and that is a CO के केस में अगर मैं बात करती हूँ तो CO that is your 4 here. So it must be remembered that the heterogeneous equilibrium of pure acids, solids and liquid must be present however small it may be, and for the equilibrium to exist, but their concentration of partial pressure do not appear in the expressions of the equilibrium constant, and in that equation we have another equation, and that we will discuss that. Another equation we have is, for example, that is Ag and O that is in the form of solid plus 2HNO3 in the form of aqueous, it will give, and of course that is 2AgNO2 aqueous plus H2O. So this will give, and for that we'll find it out the Kc here, so that Kc equals to that will be AgNO3 का whole twice was upon HNO3 का whole twice. Yeah, so this will be finding out the Kc. Now we'll move ahead with the numerical that we have to discuss here. ओके, सो फॉर दैट सेक एन के लिए मैं यहाँ पे लिख देती हूँ क्लियरली, क्योंकि वहाँ पे कॉन्सेप्ट आपका सही शायद नहीं लिखा होगा, दिख नहीं रहा है. सो दैट एन सॉलिड जो है फॉर कार्बन मोनोऑक्साइड गैस दैट गिव्स द NiCO2 एंड दैट CO4 in the form of the gases. So for that equilibrium constant we will be finding out like Kc equals to Ni, and that is CO4 upon that is CO, and that is the power of 4 here also. With regard of that, if I'm talking about so here will that, as I told you, that it may be remembered that the heterogeneous equilibrium, pure solids or the liquid must be present, and that however small it may be, but for that equilibrium to exist, but the concentrations of the partial pressure do not appear in the expression of the equilibrium constant. That in the reaction you can see that Ag2O, that is in the form of solid plus 2HNO3 aqueous, that gives to AgNO3 in the form of the aqueous plus H2O here in the form of the liquid here. So here we'll find it out the Kc is AgNO3 का whole twice upon we have HNO3, and that is of power 2 here as well. Okay, so this is what we'll find it out. So let's go ahead with another question here that we'll have to discuss, and the question we have is the value of Kp for the reaction is carbon dioxide gas plus C, that is the carbon in the solid form, and that will give you as a 3CO in the form of the gases is 3.0 at 100,000 Kelvin. If initially the P of CO2 that is equals to 0.48 bar, PCO that is 0 bar, and pure graphite present, calculate the equilibrium partial pressure for the carbon monoxide and carbon dioxide. So for this reaction, let X be the amount of the carbon dioxide reactant. So we'll have an equation that is carbon dioxide in the form of the gases plus C, that is of solid. It will give carbon monoxide in the form of the gases. So initial pressure at 0.48 bar, that is 0, what they had given you in, that they had mentioned you in the question here. Okay, so with regard of that at equilibrium, if I'm talking about, so at equilibrium, if I'm talking about start में तो मैंने बता दिया at equilibrium अगर हम बात करते हैं तो that is 0.48 minus x bar here, and for that case 2x bar as well. Okay, and for that we'll find it out the Kp here, and that is of P2, that is CO upon that is PCO4 2 here as well. And for that Kp we'll be finding out like Kp equals to 2x की power twice by 0.48 minus x, and that is equals to 3. And further we'll solve it out, 2x 4x2 that is 3, 0.48, and that is minus x. 4x2 equals to 3 is that is your 0, is that okay, that we had done 0, or when we are multiplying it out, so 1.44 minus x as well, then we will get 4x2 plus 3x minus 1.44 equals to 0. So here we'll find it out, a equals to 4, b equals to 3, and c equals to minus 1.44. So now we'll be putting this value in the this formula, that is minus b plus minus under root b square minus 4 ABC हमें already पता है, and we'll put the value, and as well as we can find it out the value as well. So here we'll just do ahead, and that I will go ahead with this with the value here as well. So here with regard of that, if I'm talking about, so we'll just find out the value. We'll put the value plus minus, that is under root 3 square minus 4, and then a is your 4 as well, and then c is your minus 1.44, and that is 2 multiply 4a, that is your 4 here. So we'll further solve it out, and then we'll find it out the value, the minus 3 plus minus, that is 5.66, and then divided by 8, and that is minus 3 plus 5.66 by 8 here as well. So yes, of course, then that as the value of x cannot be negative, hence the neglect that value which we will be having here, and because x would not be a negative, and then x equals to 2.66 by 8, and that is equals to 0.33. The equilibrium partial pressure we have is your, that is monoxide for that 2x, and that is 2 multiply 0.33. We'll just multiply and we'll get 0.66. 3 2 are 6, 3 2 are 6, 0.66 bar here. And for P of CO2, that is your 0.48, and minus x, that is 0.48 minus 0.33, and which will give 0.15 bar here as value. So with regard of that, now we'll move ahead or with further, and that will discuss more further regarding this. So we'll discuss about the applications of equilibrium constants. What are the applications of equilibrium constant be used? And before considering the applications of equilibrium constant, let us summarize the important features of equilibrium constant as follows. The first is your equilibrium constant is applicable only when the concentration of the reactant and the product have attained their equilibrium state. The second is the value of the equilibrium constant is dependent of the initial concentration of the reactant and the product. The third is the equilibrium constant is temperature dependent, जैसे equilibrium constant जो है वो temperature dependent होता है, having a one unique value for a particular reaction represented by the balance equation at a given temperature. The fourth we have is the equilibrium constant for the reverse reaction is equals to the inverse of the equilibrium constant for the forward reaction. And the fifth one we have is that the equilibrium constant K for a reaction is related to the equilibrium constant of that corresponding reaction, where the equation is obtained by the multiplying or dividing the equation for original reaction by a small integer. With regard of this, let us consider some application of the equilibrium constant too, that predict the extent of the reaction of on the basis of its magnitude, and even though predict the direction of the reaction, and as well as to calculate the equilibrium concentration. So with regard of that, the prediction will start with the predicting the extent of the reaction here. Before starting with this, the numerical value of the equilibrium constant for a reaction that indicates the extent of that reaction, but it is important to note that the equilibrium constant does not give any information about the rate of which the equilibrium is reached, and the magnitude of K and the Kp, Kc and the Kp is directly proportional to the concentration of the product, as these appeared in the numerator of the equilibrium constant expression, and inversely that is proportional to the concentration of the reactant, these appears in the denominator, and that implies that a high value of K is suggestive and of a high concentration of the product, and the vice versa as well. With regard of that, if I'm talking about, we can make that the following generalizations concerning the compositions, and concerning those compositions where we'll discuss equilibrium mixture as well. So where if the Kc is greater, like the Kc is greater than 10 to the power 3, the product predenominator over reaction, that is the Kc, is very large, the reactant proceeds nearly to the completion. Consider the following example, like the reaction of the H2 with O2 at 500 Kelvin at very large equilibrium constant, that we will be finding out that will be your Kc equals to 2.4 into 10 to the power, that is 47 here, with reference to the reaction of the H2 and the O2 at 500 Kelvin has a very large equilibrium constant, that is Kc equals to 2.4 into 10 to the power 47 here. Where if I'm talking about the H2 plus Cl, यहाँ पे मैंने बात किया था H2 और O2 के बारे में, and here we'll discuss about कि like H2 और Cl2 जो कि दोनों ही gases form में है, and when they react and then when they formate to HCl that at 300 Kelvin, so they have a Kc value that is equals to 4.0 into 10 to the power 31 here as well. With regard of this, they're not talking about the another equation, that is your H2 in the form of the gases plus Br2, that is also in the form of the gases, and it will give to Br. Okay, so at in the form of the gases here, so at 300 Kelvin, where Kc is equals to 5.4 into 10 to the power 18, where Kc is less than 10 to the power 3, -3, then the reactant predominate over the product, and that is the Kc is very small and that reactant proceeds rarely. So consider the some of the example that the decompositions of H2 and the H2 and O2 here at at 500 Kelvin has a very small equilibrium constant, that is Kc equals to, where we are talking about Kc equals to 4.1 into 10 to the power minus 48, and 48 here. And with N2 और O2 की अगर हम बात करते हैं, so N2 और आपका अगर N2 that is in the form of the gas plus O2 in the form of the gas, that will give you 2NO, and that is in the form of the gas at 298 Kelvin temperature, and has of Kc value equals to 4.8 into 10 to the power minus 31. So if the Kc is in the range of 10 to the power minus 3 से लेके 10 to the power 3, that is appreciable concentrations of both the reactant and the product are present. And consider the following example, like for reactions we have H2 and I2, that gives the HI that you also know. And for the H2 and I2, if I'm talking about, so I2 and H2 के case में that will give HI, and for that we have a Kc value that is equals to 57.0 at 700 Kelvin here. So also gas phase decompositions of N2 and O4, that 2NO2 is another reaction with the value of the Kc that we have here. For that say 4.64 into 10 to the power minus 3 at 25 degrees Celsius, which is neither too small nor too large, and hence equilibrium measure contain the appreciable concentration of both the N2O4 and NO2. Generalization that we will be illustrate here in the form of the diagram here that we have to discuss. So there is a diagram, as you can see here. This is a negligible, where reaction hardly proceed. It will go toward the Kc that 10 to the power minus 3 से लेके 10 to the power 3, जो कि मैंने अभी आपको बताया है here. Both the reactants and the products are present at equilibrium state, and where this is extremely large, where the reaction proceed almost to be the completion here. With regard of that, this is the depiction of the extent of the reaction of the Kc here. Now we'll discuss that this is the dependence of the extents of the reactions of Kc. Now we'll discuss the predicting the directions of the reaction, कि हम किस तरह से predict करते हैं direction of the reaction को. And with regard of that, we will go ahead, and here with knowing this, the equilibrium constant help in predicting the direction in which a given reaction will proceed at any stage. And for this purpose we can calculate the reaction quotient, that is Q. And the reaction quotient Q, that Q will be the molar concentration of the Q, and with the partial pressure as well, that is defined in the same way as the equilibrium constant K, except that the concentration in Q are not necessary equilibrium values. For that general equation, we have an equation that is a small a in capital A plus small b in the capital B, that will give small c in capital C plus a small d in the capital D. And for that sake, when finding out the Q here, we will get the value of C, capital D, and the small d as well, and that is of capital A and that small a, where the capital B and as well as the small b here. Then if we can say that if Q then QC is greater than QC, then the reaction will proceed in the direction of the reactant, that is in the reverse reaction. Okay. And if we can say that QC is less than Kc, so here the reaction will proceed in the direction of the product one, that will means that it will be in the forward reaction here. Okay, in terms of this. But if we say the case that where QC is equals to Kc, where the reaction mixture is already at equilibrium, so the gas state reaction of the H2 and O2, that will give you here where I'm talking about like H2 in the form of the gas plus I2 in the form of the gases, that will give to HI, and that is also in the form of the gases, where the Kc value we have 57 that is 5731 at 700 Kelvin. Okay, so here suppose we have a molar concentration, that is H2O, that is 0.1 and 0.20 for the HI2, and that HI के लिए 0.40 m, that the subscript of the subscript sign on the concentration of the symbol, that means the concentration was measured at some arbitrary time T, not necessary at an equilibrium. Thus the reaction for that question at that stage of the reaction that we will be getting. So what they had given you the value is your H2 for this at a time T, that is your 0.1 mole, and For the I2 at a time t, so they had given you 0.20 mole, and for HI, and that at a time t, that is 0.40 here. So we'll just find out the value of Q here, and we will be finding out, and that is your H of I is of T2 minus, that is pi H2 at a time t here, and as well as the I2 at a time t here as well. So we'll put the value, that is 0.40 square bond, that is 0.10, and multiply 0.20 here as well, and that will give 8.0. So now in this case the Q does not equals to the K, that is 57.0. so that mixture of H2 and I2 and HI is not at equilibrium, that is more H2 and I2 will react to form more HI, and their concentration will decrease till QC equals to Kc here. Till that the reaction of the coefficient Q is useful to predicting the directions of the reaction by comparing the values of QC and the Kc, and thus we can make that following generalization concerning the directions of that reaction, that the reactant and the product QC and QP, like that QC is smaller than QP, then we have QC is equals to Kc, and that QC is greater than Kc. This is all what this is in the form of that they are moving in the forward reaction or the backward reaction. For that we can say that if QC is less than Kc, then the net reaction goes toward from left to right. Okay, and if QC is greater than Kc, so where the reaction goes from right to left, and if QC equals to Kc, then of course no net reaction occurs. Okay, so now here with regard of this we'll discuss some of the question, and the question we have is the value of Kc for a reaction, that is 2A is gives you B plus C, or P plus C gives 2A, is 2.2 multiply into 10 to the power minus 3. At a given temperature, the composition of the reaction mixture is A equals to B equals to C is 3 into 10 to the power minus 4 mole, and in which direction the direction will proceed. You have to tell किस direction में आपका reaction proceed करेगा. Okay, so with regard of this question only, we'll go ahead and we'll solve this question, and we'll tell कि किस direction में आपका वो question solution move करेगा, reaction move करेगा. Here for this, for a given reaction, the reaction coefficient of Q is given that we'll have QC equals to B, and then of C upon A power square. Okay, so where we'll put the value as A equals to what they had given you, A equals to B equals to, and that is equals to C here, and that is equals to value of 10 to the power minus 3 mole. And for the coefficient Q, we will find it out 3 into 10 to the power minus 4 here, sorry, this is 4 minus 4, and that is multiplied by 3 into 10 to the power minus 4 as well, and divided by 3 into 10 to the power minus 4 ka whole square here as well. So with regard of that, we will get the value of 1, because QC is greater than Kc, so the reaction will proceed in the reverse direction. So reverse direction में आपकी जो है reaction वो proceed करेगी. Now we'll move ahead with another question, and that is the another topic you can say, that is the calculating the equilibrium concentration, कि किस तरह से हम equilibrium concentration को calculate करते हैं. With regard of that, in the case of the problem in which we know that the initial concentration but do not know any the equilibrium concentration of the following 3 steps shall be finished, and then we can find it out like this. Step 1 में क्या होता है, write the balance equation for the reaction. आप पहले balance equation लिखते हो, इसमें हम लिखेंगे भी next steps में. And second up step होता है कि under that balance equation make a table that list for each of the substance involved in the reaction, that is the initial concentration, second is the change of the concentration ongoing the equilibrium, and the third is the equilibrium concentration as well. In constructing the table, define that X as the concentration mole later in inverse. and to one of the substance that react on going to the equilibrium, then use the stoichiometry of the reaction to determine the concentration of the other substance in the terms of the x. And step 3 जो है, that is the substitute the equilibrium concentration into the equilibrium equation for that reaction to solve the value of x. And if you are to solve a quadratic equation, choose the mathematical solution that make the chemical sense as well. Then the fourth step में हम calculate the equilibrium concentration from the calculated value of x. And then after that, in the fifth one here, that check your result by substituting them into the equilibrium equation. So now we'll go ahead with this question and then we'll solve this. The question we have is your 13.8 gram of N2O4 was placed in a 1 liter of reaction vessel and at 400 Kelvin, and all that is around to attain the equilibrium here. And that N2O4, it gives to NO2, and we can say that 202 gives to N2O4, and the total pressure of the equilibrium was found to be 9.15 bar. Calculate the Kc, you have to calculate Kp, and the partial pressure at the equilibrium here. So this is not that much easy, but that much not tough. अगर आप कर रहे हो, अगर आपको थोड़ा सा भी इसके बारे में knowledge है, then you will be able to do in an easy way as well. With regard of that, if I'm talking, we know that the value that is your PV equals to N or T, you know very well. And the total volume what they had given you is, your volume is 1 liter here, but they had molecular masses of N2O4, that is N2O4 का molecular masses जो है, that is 92 gram. Number of moles जो है, number of moles what they had given you is your 13.8 gram per 92 gram. So what we will be finding out, that is 0.15, and that is 0.15, that is 0.15 of that gas in and that the gas constant, we have a gas constant, we will be having a gas constant, that is the value of R. Okay, and that is 0.083 bar liter mole inverse Kelvin. And then we have a temperature, and the temperature we have, temperature is equals to 400 Kelvin, and we know the value of PV equals to nRT. We will write the value and we'll just solve it out. So P multiply 1 liter volume, we have no 1.15 mole into 0.083 bar liter mole inverse Kelvin multiply 400, जो कि टेम्परेचर दिया हुआ है Kelvin here. So what we'll find it out, P equals to, that is 4.98 bar. So initial pressure जो N2O4 का था, that is 4.98 bar था initial N2O4 का. and अब जो बाद में है F212 का, अभी वो तो मेरे को नहीं पता, वो तो भी 0 दिखा रहा है. ओके, एंड इक्विलिब्रियम ऑफ 4.9 इक्विलिब्रियम बार में अगर हम लेके चलते हैं, तो इसको फिर हम लेके चलेंगे 4.98 इक्विलिब्रियम की कंडीशन पे. इक्विलिब्रियम पे क्या लेके चलेंगे, at equilibrium we will take a 4.98 minus x bar, and for 2NO2, and that will be the 2x bar. So now we'll find out the value here. So here for this we have PFN's P total at an equilibrium, that P of N2O4 plus P of NO2, that we will be having as your 9.15 equals to 4.98 minus x plus 2x, and that is 9.15 equals to 4.98 plus x, and that is x equals to here, and we can say that x equals to, and that is x equals to, we will be having 9.15 minus 4.98 here, and that will be give 4.17 bar. So partial pressure for that equilibrium we have for P(N2O4), and that is equals to 4.98 minus 4.17, that will give 0.81 bar. And for P of NO2 here, and that will give 2x, and that will be 2 into 4.17, that is 8.34 bar as well. With regard of that, we'll be having Kp equals to P of NO2 whole twice plus PN2O4. Then we'll find out the value here, that will be 8.34 ka whole square upon 0.81, and that is equals to 85.87 here. And for that sake, we will be finding out the Kp value, and that is Kp equals to that is Kc or T, and that is of delta n, and we'll find it out this value here. Kp जो है that is 85.87, that what we had find it out, and equals to Kc 0.083 multiply 400 and power of 1, and then we'll find out the Kc, that is equals to 2.586, that is equals to 2.6, near about approximate value. We'll find it out here. With regard of this was an important question as well. Now we'll discuss one more question, and that is the last question of the session as well. Then we end up with this class as well. So for this is the question, that is the last question, that is 3.00 mole of PCl5 kept in a 12 closed reaction vessels as allowed to attain equilibrium at 380 Kelvin, and that calculate the composition of the mixture at an equilibrium, that is at equilibrium, that is Kc equals to 1.80 here. So the reaction we have is PCl5 that gives PCl3 plus Cl2. Initial concentration we have here, that is initial concentration we have 3.0, and here 0, and then here 0, and let x of that PCl5 be the dissociated at an equilibrium, and at equilibrium it will be 3 minus x, and this is x, and as well as x, that is at equilibrium here. And now we'll find out the value as well, and that is of K equals to PCl3 Cl2 upon PCl5. So we'll put the value 1.8 x square upon 3 minus x. Further we'll solve this. What we'll get is your x2 plus 1.8 x minus 5.4 equals to 0. We'll find out the value here, that is x equals to minus 1.8 plus minus, and that is under root 1.8 ka square minus 4 minus 5.4, that is upon 2 here. But then we have another one, and that is x equals to minus 1.8 plus minus under root 3.24 plus 21.6 by 2. Now further solving on this, then we have x equals to minus 1.8 here, and that is a plus minus, that is your plus minus 4.898 and upon 2 here, and then further we'll have x equals to 1.8 plus 4.98, and that is upon 2, and we'll find out 1.59. This is the x value, that is 1.59. Moreover, more further we'll solve this, then what we'll get, we'll find out the value here, that is PCl5, and that is equals to 3.0 minus x here, and that is 3 minus 1.59, that is equals to 1.41 mole here. With regard of that, PCl3 we have Cl2 as well, and that is x equals to 1.59 mole here. So this is how you will find it out, and that is the solution that you have to find it out here. With regard of that, we'll continue with the next class, that is the relationship between the equilibrium constant and the reaction question Q, and the Gibbs energy as well, that is represented by the G. Moreover, in this chemistry, if I'm talking about, we had in the last unit, and we have covered up most of the last first, second, third, fourth, fifth unit as well. In the respect to the first unit, what we had discussed in the some basic concepts of chemistry were the importance of chemistry, nature of matter, properties of matter and their measurements, uncertainty in measurements, laws of chemical combination, Dalton's atomic theory, atomics and molecular theory, mole concepts and molar masses, percentage composition, stoichiometry and the stoichiometric calculation as well. That's what we had done in the unit 1. Unit 2, we have done structure of atoms, that is subatomic particles, atomic models, developments leading to the Bohr's models of atom, and as well as Bohr's models of the hydrogen atom towards the quantum mechanical model of an atom and the quantum mechanical model of an atom as well, that we had discussed here. In the unit 3rd, what we had done is the classification of the element and the periodicity in the properties, that is why do we need to classify the element, genesis of the periodic classification, modern periodic table and the present form of the periodic table as well, and the nomenclature of the element with atomic number that is greater than 100, electronic configuration of element and the periodic table, electronic configuration and the types of element, S block, P block, D block and F block as well. And even though we had discussed the periodic trends in the properties of element as well. Now in moreover, if I'm talking about, so we have to discuss the unit 4 that we had discussed as well in reference to the unit 4, unit 5, unit 6 and unit 7. This is the unit that we are discussing here, that is your unit 7, that is of equilibrium here. And before that we had discussed thermodynamics as well, and that is also an important one with regard of the questions that we have to do. Okay, so here in the further cases, if you have any doubt, you can just go on in the comment section, you can just inform it out. In the unit 4, that the chemical bonding and the molecular structure, that is the Clausius-Lewis approach in the chemical bonding, ionic and the electron valence bond parameters, the valence shell electron pair theory, that is the whisper theory, valence bond theory, hybridization, molecular orbital theory, bonding in the some homonuclear diatomic molecules, and the hydrogen bonding that we had done here. With regard of that, unit states of matter, that is unit 5, that is the intermolecular forces, thermal energy, intermolecular forces of the thermal interactions, the gaseous state, the gases law, ideal gas equations, kinetic molecular theory of the gases and the behavior of the real gases, deviations from the ideal gas behavior and the liquefaction of the gases, and the liquid state that we had discussed here. After that, unit 6 we had discussed, that is the thermodynamics, thermodynamic states, application, measurements of delta U and delta H, calorimetry, enthalpy change, delta R of H of the reaction, enthalpy for a different types of reactions, spontaneity, Gibbs energy changes, and the equilibrium that we had discussed here. In the unit 7 we had discussed equilibrium, equilibrium in the physical process, equilibrium in the chemical process, dynamic equilibrium, laws of the chemical equilibrium and the equilibrium constant, and homogeneous equilibrium and heterogeneous equilibrium that we had discussed here. And the application of the equilibrium constant we had discussed. In the next coming classes we'll discuss the relationship between the equilibrium constant K and the reaction coefficient Q and the Gibbs energy G. Then we'll discuss the factors affecting the equilibria, ionic equilibria in the solutions, acid, bases and salts, ionizations of solids, acids and bases, and buffer solution. Then we'll discuss the solubility equilibria of the sparkly soluble salts here. Then we'll end up with this class and we'll end up with chemistry, and further we'll discuss about the organic chemistry as well. So class आज के लिए इतना ही. Thank you, hope you enjoy this video. If you like this video, please give a thumbs up and give a suggestion on a comment box. Please like, share and subscribe our channel so that many and maximum people can get the information at once, and even though you can also enjoy the video as well. Thank you.